Welcome to Math 2318, Section 5.3. We're looking to see if we can diagonalize a matrix A. So A is P, D, P inverse, where D is the diagonal matrix. We have here P, and we can find P inverse. What they want us to figure out is a to the fourth power. Alright, well, let's see. A to the fourth power is a times a 4 times. And each one of these is P, D, P inverse. Well, the P inverse P pieces all collapse. They are the identity. And so a to the fourth power is simply P times D to the fourth power times P inverse. Now I'm going to need P inverse in just a minute, so let's talk about that. P inverse we had from a formula before, and that was it was 1 over the determinant of P. Well, the determinant of P here is 5 minus 6. So I get a negative 1 from this part. So that part is a minus 1. And then to get the inverse part, we swap these two on the diagonal. So a 5 and a 1. And then you have the negative of the other two. And this was our simple formula for A inverse in the 2 by 2 case. So we're going to need that in just a moment, because when I get a to the fourth, I'm going to need P d to the fourth times P inverse. Alright, so let's see, what about d to the fourth? Well, d to the fourth looks like the following. But if you trace this out, because D only consists of diagonal elements, D to the fourth power is pretty straightforward. It's just each of the diagonals raised to the fourth power. So A to the fourth power is going to be P, so here's P, D to the fourth power, and here's P inverse. And so, multiplying these two together, I first took P times D to the fourth, and then from there multiplied it by P inverse to give us the final answer for A to the fourth power. Alright, in problem 2, they tell us A, here's A, is factored into P, D, and P inverse. It turns out that the diagonal elements on D are actually the eigenvalues for the original matrix. So they are 5, 1, and 1. Even more importantly, we get the basis. For the eigenvalue of 5, this is the basis in the first column. That's where the 5 is. 1 is in the second column, and this 1 is in the third column. So we actually find the corresponding basis vectors for each of the eigenvalues. Okay. In question 3, we want to diagonalize this matrix if possible. Alright, so first off, I need to figure out what are the eigenvalues of this matrix. So let's see, find the determinant. So 6 minus lambda times minus 6 minus lambda. Alright. The upward diagonal there is 0, so I get nothing from that. So it's already factored equals to 0. So I get answers of 6 and minus 6. Alright, so that's my D, my diagonal with the eigenvalues down the diagonal. And so now I need to find the basis vectors for each of the eigenvalues. So for lambda equals 6, I need to solve a minus 6i x equals 0. So simply form it, and in this case it's already pretty much solved. x2 is free. x1 is a 6/5 x2. Now, to make it look nicer, multiply through by 5 to get our first column vector for lambda equals 6. Repeat the process for lambda equals minus 6. Alright, so again, not a lot to try to solve. I get x2 is free, x1 is 0. Alright, so in that case, for lambda equals minus 6, I get 0 and 1. And so here is P, the P that's multiplied by D times P inverse, and that will diagonalize matrix A. Alright, so in question 4, we have a new matrix. We'd like to diagonalize it. Let's see if we can. So I go about looking for the determinant to figure out the eigenvalues. Alright, downward diagonal minus the upward. And so in this case, because of the way our original matrix looked, I only get one eigenvalue. Alright, well, plug that in now. So a minus 9i. And we get this vector, and so that tells me x1 is free and x2 is 0. But I only have one eigenvector, and I'm in R2, and so I don't have enough, and so therefore A cannot be diagonalized. Alright, in question 5. They are giving us, here's matrix A, they're giving us already the eigenvalues. And so what I need to figure out would be what would be the columns or the eigenvectors for matrix P. So use lambda equals 4, and we solve this particular system. Not very hard to solve because it falls apart quickly. And so what I get is x3 is free, x2 is free, and x1 depends upon x2 and x3. Splitting it up, I get x2 times 4, 1, 0, and x3 times minus 2, 0, 1. So we get two column vectors for that single eigenvalue. I repeat the process for lambda equals 7. And again, it's fairly straightforward to solve. And I end up getting x3 is free, x2 is x3, and x1 is x3. And so we get our last column vector for that eigenvalue. And so D has the eigenvalues 4, 4, and 7. And P then is minus 2, 0, 1, 4, 1, 0, and 1, 1, 1. Now you might say, well, why did they get minus 3, minus 3, minus 3? It's exactly the same. They just took this column and multiplied everything by minus 3. Why? I don't know. You could have had 2, 2, 2 if you wanted, just as long as they're all the same. And so that concludes this particular section on diagonalizing our matrix.